In this section, we discuss power series. Power series is a special type of series that has many applications to science and engineering. And the most important thing here is that it provides a way to represent some of important functions. For example, sine, cosine, tan function, and many other functions can be represented as polynomials. And that makes dealing with issues like convergence and many other issues that arise in when we study that special type of functions that make the treatment easier. So what do we mean by power series? A power series is a series that can be written in this form: series of Cn times x minus a raised to power n, where Cn are constants and x is a variable. So this is the first time we meet with a series that involves x as a variable. X is real number. So this is a special type of series. If we expand this by substituting finding some terms, let's substitute n equals 0, we get c0 times x minus a to the power 0, but x minus a to the power 0 is just 1. Plus, substitute 1, you get c1 times x minus a to the power 1. Substitute 2, c2 x minus a to the power 2, etc. And as we can see, we have here terms that involve constant multiplied by some variable, or x minus a variable minus a. A is called the center of the series. So this is a series centered at x equals a. Now this series is convergent at a. It's convergent, always convergent at x equals a, because if you plug in a here, if we plug a into the series, we get 0, and that means it's convergent. Now here, when we deal with the power series, we have three cases, or three possibilities. The first possibility is that the series is convergent only when x equals a. And in this case, we call the radius of convergence equals 0, but we'll talk about radius of convergence later. Or we have the series is convergent for all x real numbers. The third case is that there exists, or there is, positive r natural real number such that the series is convergent if x minus a, the absolute value of x minus a, is less than this r, and divergent if the absolute value of x minus a is greater than r. Now r in this case is called radius of convergence. Radius of convergence. We will learn how to find it. And so for the first case here, convergent, if the series is convergent only when x equals a, in this case r is equal to 0. The radius is 0, so we get 1 point, x equals a. And for the second case, for all x, that means r equals infinity. That means the interval has infinity endpoints. And the third case, we have one of the two cases, either x minus a absolute value less than r or greater than r. If it's less than r, then it's convergent, otherwise it's divergent. Now let's take some examples. Now the first example is that we want to find for what values of x is the series n factorial x to the nth and from 0 to infinity convergent. Now we usually start with the ratio test. So to test this convergence, we use ratio test. So the ratio test says that the limit as n goes to infinity of an plus 1 over a sub n should be less than 1 in order for the series to be convergent. Now let's compute this. This is limit as n goes to infinity of n plus 1 factorial here times x to the power n plus 1 divided by an. This is an. The original general term is a sub n. And then we simplify. We can do n plus 1 factorial. We can write it as n plus 1 times n factorial. And we discussed this case in a previous video. So this is multiplied by x to the power n times x to the power 1 here, this term or this expression, over n factorial times x to the n. And then we simplify. We can cancel n factorial and we can cancel x to the n. So we get absolute value of n plus 1 times x under the absolute, this is under absolute value. So since n plus 1 is positive, we don't need, now we still have infinity here. Since n is positive, we can pull it out of the absolute value. So we have limit as n goes to infinity, n plus 1 times absolute value of x, because x can be positive or negative or 0. So since it can take positive or negative values, we still have absolute value. Now if we take limit as n goes to infinity, just substitute n goes to infinity here, you get infinity for any value of x except x equals 0. So this is not equal to, this is equal to infinity. So the series is divergent for x not equal to 0, for any value different from 0, and it's convergent only when x equals 0. Well, let's take another example. If we want to find the radius of convergence of the series x minus 3 to the power n over n from 1 to infinity, we apply the ratio tests. So we have limit of a sub n plus 1 over a sub n, n goes to infinity. This is limit as n goes to infinity of absolute value x minus 3 to n plus 1 over n plus 1 times, now when we divide by a n, we flip it, we get n over x minus 3 to the power n. Now we simplify. We can cancel x minus 3 to the nth with the n, and we have limit n goes to infinity of absolute value x minus 3 times n over n plus 1. And since x minus 3 does not depend on the limit, we pull it out of the limit. So absolute value x minus 3 times limit n over n plus 1. We don't need absolute value for n over n plus 1 because it's positive, because n takes values from 1 to infinity. Now the limit of this is equal to 1. You can apply the L'Hopital rule. Derivative of the numerator is 1, derivative of the denominator is 1, 1 over 1 is equal to 1. So we have x minus 3. Now in order to determine the convergence of this series, if this is less than 1, then it's convergent. So this one here is r, the radius of convergence. Because as you may remember, here if you look at this formula, x minus a less than r, we wrote x minus 1 less than 1, or less than 1, yeah, x minus 3 less than 1. So 1 is the value of r, the radius of convergence. Now after that, we can determine the interval where the function is, where the series is convergent. So x minus 3 is, we rewrite this without using absolute value notation. So absolute value x minus 3 less than 1 is x minus 3 is between -1 and 1. And then we solve for x is between 2 and 4. So in this interval, it's convergent. The series is convergent. But we need to check the endpoints so that we can either include them or exclude them from that interval. So we check the endpoints. So we start with x equals 2, the first endpoint. So we plug this into the original series. It's the series x minus 3, x is 2, 2 minus 3 to the power n over n, and from 1 to infinity, and this is series -1 to the power n over n, and from 1 to infinity. Now we take the absolute value of this in order to study the convergence of this series, alternating series. We take the absolute value of -1 to the power n over n, and we find that this is equal to 1 over n. This is absolute value test, but this is always the right hand side series. This series is harmonic series. It's p series with power 1. It's called harmonic series, and actually this is p series. It's always divergent. We know that the p series is divergent when p is equal to 1. So if the larger series is, if this series is divergent, the absolute value is divergent, that means we have the original series is divergent. So we can't exclude include x equals 2. Let's check x equals 4. X equals 4, absolute series of 4 minus 3 to the power n over n, and from 1 to infinity. This is series 1 to the power n over n, and from 1 to infinity. But 1 to the power n is 1 over n series. This is also a harmonic series. It's divergent. So that means the series is convergent on the interval, open interval 2, 4. Another example, we have the series n times x plus 2 to the power n over 3 to the power n plus 1, n from 0 to infinity. And in this case, we want to study the convergence. so the interval where this series is convergent. So we apply the ratio test. We have limit as n goes to infinity of absolute value of n plus 1 times x plus 2 to the power n plus 1 over 3 to the power n plus 1 plus 1 times the reciprocal of the original nth term. So it's 3 to the n plus 1 over n times x plus 2 to the power n. Now we try to simplify. It's better to rewrite the terms or the expression this way. We have n plus 1 and we have n here, so n plus 1 and n, and we have x plus 2 to the power n plus 1 over x plus 2 to the power n times 3 to the power n plus 1 over 3 to the power n plus 2. I just reordered the expressions inside the absolute value. Now we can simplify. We have n plus 1 over n times. Now we can cancel this with n and we get x plus 2. And then we can simplify this. So 3 to the n with 3 to the n, and we are left with 3 over 3 squared, which is 1/3. So the limit becomes 1/3 times absolute value x plus 2, because the limit does not depend on x, times limit as n goes to infinity of n plus 1 over n. And we know that this is equal to 1. So this is convergent if 1/3 x plus 2 is less than 1. Convergent if this is true. Now we need to write it as x minus a less than r. So we need to multiply both sides by 3. So we have x plus 2 is less than 3. Now it's written in this form. So a is 2. R is 3. This is the radius of convergence. Now we want to find the interval where, on which the series is convergent. So we need to solve this to rewrite it without using the absolute value notation. So it's between -3 and 3. And then we subtract 2 from each term or each side. -5 to 1. So the series is convergent on this interval. Now we need to check the endpoints. We start with x equals -5. When x equals -5, we need to substitute this into the original series. We get series n from 0 to infinity, n times -3 to the power n over 3 to n plus 1. And this is series -1 to the power n, because here we have -1 to the power n times 3 to the power n times n over 3 to the power n plus 1. Now we can simplify more. So we get series -1 to the power n times n over 3. And since 3 is constant, we can pull it out of the sum. -1 to the power n times n. Now if we take the absolute value of this series, absolute value of -1 to the power n times n, and from 0 to infinity, this series is equal to the series n, and from 0 to infinity, because -1 to the power n is equal to 1 inside the absolute value. So we have 1/3 here. So this is divergent. This is divergent. For example, substitute 0, substitute 1, 2, 3, as you can see. It's divergent. That means it goes to infinity n over 3 goes to infinity as n goes to infinity. So it's divergent. So we can't include this point x equals -5 to that interval, the interval of convergence. Now we need to test the other endpoint, x equals 1. We have the series n times 3 to the power n over 3 to n plus 1, n from 0 to infinity, and this is series. If we simplify, we get n over 3, n from 0 to infinity, and this is divergent. So as n goes to infinity, n over 3 goes to infinity, so it's divergent. So the interval of convergence is -5, 1. It's open at -5 and open at 1. Now the last example, we have the following series, the series -3 to the power n, x to the power n over square root n plus 1, n from 0 to infinity, and we want to find radius of convergence r and interval of convergence. So we apply a ratio test as usual. So we have limit a n plus 1 over a n, n goes to infinity, and this is limit as n goes to infinity of -3 to the power n plus 1, x to the power n plus 1 over square root n plus 1 plus 1 times the reciprocal of a sub n. This is a sub n. Reciprocal of this is square root n plus 1 over -3 to the power n x to the power n under the absolute value. Now we need to simplify this. So it's better to reorder the expression. So we have -1 to the power 3 to the power n plus 1, and we have 3 to -1, or -3 to the power n, times, now we have x to the power n plus 1 in the numerator and x to the power n in the denominator, and we have square root n plus 1 in the numerator, square root n plus 2 in the denominator. Now we can simplify. We get, if we simplify, we get limit n goes to infinity of, now what is left here is that, now we can cancel this with this, we get -3 to the power 1. So -3 times, now we cancel this with this, x times square root n plus 1 over square root n plus 2, and then this is limit, now absolute value of -3x is just 3 absolute value of x, n goes to infinity of square root n plus 1 over square root n plus 2. We know that this limit approaches is equal to 1 because the expression approaches 1. As you can see, n we have same power of the expression. I mean, you can do it this way. You have square root n plus 1 over square root n plus 1. We can deal with the dominant terms from numerator and denominator, so that's square root n over square root n, which is equal to 1. Or we can apply the L'Hopital rule. Now this series becomes 3x. So this is convergent if this is equal less than 1. Convergent, the series is convergent if 3 times absolute value of x is less than 1, but we need to write it in the form x minus a less than r. So we still have 3 here, so we divide both sides by 3. We get x is less than 1, and actually this is written in this form because a in this case is 0. This is x minus 0, absolute value x minus 0 is less than 1, so 1 is the radius of convergence. Now we need to find the interval on which the series is convergent. Now the interval, for that reason we need to, actually I made a mistake here, this should be 3, because when we multiply by 3, we divide by 3, it's 1/3. So absolute value x is less than 1/3. We wrote it as x minus 0 under absolute value is less than 1/3. 1/3 is the radius of convergence. Now the series is convergent on the interval negative, or where x is between -1/3 and 1/3. I rewrote this without using the absolute value notation, and you need to remember that absolute value of x is less than a. We can rewrite it without using the absolute value notation as negative a to a. I mean x is between negative a and a. Now we need to test the endpoints. So we check endpoints. X equals -1/3. So the series become, when we substitute x equals -1/3, becomes -3 to the nth, -1/3 to the nth over square root n plus 1, and from 0 to infinity. And this is, after simplifying this, we get the series, as you can see, this is equal to -3 to the power n, and here 1 over -3 to the power n. We cancel these, we get 1. The numerator is 1 over square root n plus 1, and from 0 to infinity. Now using the comparison test, we can compare this with known series. So this is less than or equal to the series 1 over square root n. The denominator is smaller, that means the expression is larger. So, and we know that this series can be written as 1 over n to the 1/2. So p is 1/2. This is p series, and since p is less than 1, it's convergent. And is less than 1, that means divergent. Now this series is divergent, that means this value, we need to exclude this from the interval. Now what about x equals 1/3? For x equals 1/3, the series n 0 to infinity, -3 to the power n times 1/3 to the power n over square root n plus 1. Now we simplify the similar way. As you can see, this becomes -1 to the power n, because we have negative sign raised to power n, and 3 to the power n times 1 over 3 to the power n. We cancel these and we get the series -1 to the power n over square root n plus 1. Now this is alternating series because of the presence of this -1 to the power n. And thus we can apply the alternating series test. Alternating series test. It says first the limit of 1 over square root n plus 1. I mean bn. Where's bn? bn is this expression, 1 over square root n plus 1. So that means we ignore the -1 to the power n, and what's left is bn. So limit of bn as n goes to infinity is 0. So the first condition is satisfied. The second condition is that the series should be bn should be decreasing. So the series is bn is 1 over square root n plus 1. Now just substitute some values of n. N starts from 0. So we have 1, then 1 over square root 2 and then 1 over square root 3. As you can see, the denominator gets bigger and bigger. That means the series gets smaller and smaller, or I mean the terms get smaller and smaller. That means it's decreasing. Now since it's decreasing, those two conditions are satisfied, so the series is convergent. And that means we need to include x equals 3 to our interval. So our interval was x from negative 1/3 to 1/3. So we write here the series negative 3 to the power n, x to the power n over square root n plus 1, n from 0 to infinity, is convergent on the interval negative 1/3. It's open from negative 1/3 because at negative 1/3 it's divergent, to positive 1/3 it's closed at 1/3 because it's included, and the series is convergent.